If you stand next to a campfire, you feel the intense heat. Take 10 steps back, and the temperature drops. This is a basic rule of thermodynamics. The further you move away from a heat source, the cooler your environment becomes. For a long time, astronomers assumed our sun followed this same logic. The sun's visible surface, known as the photosphere, simmers at a predictable and relatively cool 10,000 degrees Fahrenheit. But look at what happens here. As you move away from the surface and travel 1,000 miles outward into the solar atmosphere, the corona, the temperature doesn't drop. It violently spikes to 2 million degrees Fahrenheit. The atmosphere is nearly 200 times hotter than the surface below it. This contradiction remains one of the most perplexing unanswered mysteries in modern astrophysics. The puzzle started in 1869. At the time, the only way scientists could observe the sun's outer atmosphere was during a total solar eclipse, when the moon blocked the light from the star's main body. Early astronomers used spectrometers like this one to study that glowing halo. Spectrometers are optical instruments that separate incoming light into individual wavelengths, allowing scientists to identify the exact chemical composition of a light source. When they analyzed the corona, they found a strange green spectral line. It didn't match hydrogen, helium, or any other known element on Earth. They concluded they had discovered something entirely new, and they named it coronium. It took 70 years to realize coronium was actually normal iron. The iron had simply been ionized 13 times over. Ionization is a process where extreme heat physically strips negatively charged electrons away from an atom. Stripping 13 electrons from a single iron atom requires massive amounts of energy. The calculation of that energy requirement provided the evidence scientists needed. The corona was indeed operating at 2 million degrees. The coronal heating problem was officially open. To find this heat source, we look inside the star. The core operates in hydrostatic equilibrium, balancing gravity's inward crush and nuclear fusion's outward push. This energy radiates through a dense layer. In the convection zone, superheated plasma rapidly boils, carrying heat upward. This violent boiling of electrically charged plasma acts like an immense dynamo. The churning motion generates the sun's massive, tangled magnetic fields. The sun's interior is a highly active magnetic engine. These magnetic forces eventually erupt outward, powering the extreme events we see on the surface. When these magnetic fields burst through the visible photosphere and into the corona, they release trapped energy. Astrophysicists have narrowed down how this transforms into heat to 2 leading theories. Suspect 1. Alpha waves. These magnetic ripples travel along field lines, physically pushing and accelerating charged particles to generate heat. Suspect 2. Nanoflares, or magnetic reconnection. Twisted field lines cross, build tension, and explosively snap like rubber bands, dumping heat into the corona. We cannot solve this debate from Earth due to a distance problem. It takes the solar wind 4 days to travel the 93 million miles to our planet. Upon arrival, the distinct fingerprints of waves or flares have mixed into a homogeneous soup. Pristine evidence requires proximity. Astronomers realized they could never prove which mechanism is heating the corona by analyzing degraded plasma from Earth. That requirement led to NASA's Parker Solar Probe. It is a spacecraft custom-built to fly directly into the sun's atmosphere and sample particles mere moments after they've been heated. Swooping within 3.9 million miles of the solar surface, the probe acts as a thermometer inside the corona. The FIELDS experiment measures magnetic forces to detect alpha waves, while SWEEP captures electrons, protons, and helium ions, atoms stripped of electrons, to measure their speed. By simultaneously measuring the magnetic fields and capturing the physical plasma a fraction of a second after heating occurs, the probe can definitively record the unique signature of either waves or nanoflares. This research has immediate consequences for life on Earth. Coronal dynamics dictate the severity of space weather, including the geomagnetic storms that interact with our atmosphere and threaten our power grids. Beyond our own neighborhood, the sun serves as a baseline model for distant, potentially habitable stars that we can never physically visit. Furthermore, learning how these superheated plasmas behave allows scientists to model similar conditions in distant galaxy clusters or around the edges of black holes. Plunging a probe into a star resolves a 150-year-old astrophysical mystery and provides the data needed to reconcile our observations of the sun with the fundamental laws of physics.